Welcome to Survey Matters with Duncan-Parnell. My name is Mark White. I'm the Training and Support Manager for DP. Today, we're going to get back to basics, so we're going to start with RTK. But first, please like and subscribe. All right, so on this edition of Survey Matters, I want to get back to basics. And when I say I'm getting back to basics, I want to kind of cover a couple of topics in a series that we're going to do on what is RTK and how does it work, what are robotic total stations and how do they work, and then we're going to follow those up with playlists of getting started guides. So how to configure RTK systems and go out and do a survey with them, and then how to configure your robotic total stations and go out and do a survey with them as well. So be sure you subscribe to our channel, and when you do subscribe, check the bell to turn on notifications so you'll get notified as we release these getting started guide playlists for you, all right? So keep an eye out for that. But today we're going to talk about RTK. What is it? Kind of give you a 50,000 foot view of how it works, and then talk about some of the various Trimble equipment that we have that can help you get the job done doing RTK surveys. All right, so what is RTK? Stands for real-time kinematic, if you hadn't heard that before. It's a satellite positioning technique that uses one GNSS receiver as a base station that sits on a fixed point that receives satellite information and sends that satellite information along with its coordinates, since it's sitting on a fixed point, sends that information via a modem like a radio or over the internet to another receiver that acts as a rover that's moving around and collecting 3D positions on the Earth. And it can do this in real time. That's where the real time comes from. It's kinematic because the rover's moving around, and it does it at centimeter level precision, all right? So through the use of two receivers, errors that are inherent in GPS measurement are able to be corrected, and we can get that centimeter level precision here on the face of the Earth. So let's take a quick look at the signal that we're actually receiving with our GNSS receivers from the satellites, okay? And GNSS, if you don't know, stands for Global Navigation Satellite Systems. So we call these GNSS. When I started with these, the only one around was GPS, the US system for Global Positioning System. And so I might say GPS every now and then, but nowadays, since we have four constellations, the US system, the Russian system, the GLONASS system, the European Union Galileo system, and the Chinese Beidou system, we call it the Global Navigation Satellite System now, okay? But the signal that's coming from the satellites down to the receivers starts with what's called a carrier wave, okay? And that's what's being generated from the satellite. You see the graphic there, looks like a sine wave. That's being generated using an atomic clock on the satellites, so it's very, very accurate, and that's being sent down to the receiver. And on that carrier wave rides different codes. Different codes are modulated onto the carrier wave. So you've got the CA code, or the course acquisition code, which is about 293 meters long. So just like the name implies, it's a course code. It's got numbers and time and letters on it that can be identified, but it's very coarse. It's 293 meters long before it repeats again. Then you have what's called the P code, the precise code. It is more precise. It's 10 times better than the CA code, but that leaves it at 29.3 meters long. So it's still a fairly long message there that's coming down with that code. And then you have the nav code. That's your navigation information from the satellites. So that contains things like orbit parameters, satellite health, and ephemeris data about the satellites, basically telling you where the satellite is and if it's healthy or not. All right. So you have the carrier wave that's being generated by those atomic clocks. Very accurate. Here you'll see up there it says L1 carrier wave is 19 centimeters long. There's various different carrier waves, different frequencies that are being broadcast by the satellite. L1, L2, L3, L4, and L5 are common with the US satellites. And they're like 19, 24 centimeters long. They're much shorter than those codes, okay? So how do we actually measure using that information that's coming from the satellite to the receiver? Well, the first way is what's called code ranging, using that CA code and that P code to get a location here on the Earth. And what we're doing is we're actually ranging from the receiver to the satellite, getting a distance to that. And then if we get enough of those distances, we can calculate a position on Earth. So a code, like we talked about, is being sent from the satellite to the receiver. The receiver actually has a code generator built into it as well. So it's generating the same code. And then we can take that information and kind of go back to elementary school and plug that into a little word problem. Distance equals rate times time, right? So to get the distance from your receiver back to a satellite using the code, we need the rate, which is a given. It's the speed of light. That's how fast that signal travels from the satellite to the receiver, the speed of light. And then we can measure the time difference between the satellite code and the receiver code. If you look at the little graphic here on the bottom of the screen, the satellite's sending the code on the carrier wave. The receiver is generating that same code. And what it does is it finds common points in the code and then checks the time difference. Like I said, that code's timestamped. This is generating code. It has a clock on it too, not as accurate as the clock on the satellite, because the satellite has an atomic clock. This just has a regular old quartz clock. So there's going to be some error there, but it checks that timestamp, calculates the time difference, and multiplies the rate, the speed of light, times the time, and that gives us a range from the receiver back to that satellite. And it can do that for every satellite that it sees, right? And so if we look at this graphic, as long as we have at least 4 satellites, we can get a unique position on the Earth, right? Because if we have a range from the receiver back to the satellite, we've got 1, 2, 3, and 4, and you'll see there's a ball around each one, or a radius. That radius is the range calculated using that code from the receiver back to 1 satellite, 2 satellite, 3 satellite, 4 satellite. If we take those radiuses and intersect them, there's only one spot on the Earth that those can actually intersect. So that gives us a fairly precise position. If you've got 20 satellites out there, they're all going to intersect at one spot on the Earth based on that range that we calculate from the code. Okay, but remember, course acquisition code, 293 meters long before it repeats. Precise code, better, 10 times better, but still 29.3 meters long. So there's a little bit of error in there. And normally the code range is going to get you within 1 to 2 meters. But as surveyors, we need centimeter level accuracy, right? So how do we get to that centimeter level? Well, don't forget about the carrier wave. Remember, it's only 19 centimeters, 24 centimeters long, much more precise. So the thing that separates your survey grade receiver from the GPS of your phone is the ability to calculate ranges using the carrier wave. So again, the wavelength is known, that's a given, but the total number of wavelengths is unknown. That's a phase ambiguity, if you will. You've got that phase cycle of the wave. That's an ambiguity. We don't know the whole number of waves back, because when you turn on your receiver, you're going to get a partial wave. Then you're going to start receiving whole waves. So you get a fractional amount, then you start getting whole waves. And what we have to do, or what the receiver has to do, is calculate the number of whole waves from here back to the satellite. Since the length is known, then it can calculate a very accurate range using that. Now, to do that, you have to have 2 receivers. Phase ambiguities can be fixed using differential measurements between 2 receivers, okay? That's pretty high-level math. I'm not going to get into that, but that's really what sets survey-grade RTK apart from other GPS receivers. And when we're able to solve those phase ambiguities using 2 receivers, we get centimeter-level results in the field. All right, so let's take a look at some of the other errors that are involved. So first, we solve for those, we can get the range from the code. We solve the phase ambiguities for the with the carrier wave, and that gets us down to centimeter level. But how do we get rid of some of the other errors, or what are some of the other errors that are inherent in GPS measurement? So first up here, I've got a couple of satellites and a couple of receivers, right? Because we're using 2 receivers for a base rover. We use 2 receivers to get to solve for that carrier wave as well. We've got an error up there called P. That's position of the satellite. So positional error. Remember that nav data, right? The satellite sending us information of where it's supposed to be, but it's actually moving around a little bit in space. It's never actually where it says it is. So there's a little bit of positional error. Also, there's T next to the satellite for time error, right? Satellites have very accurate clocks on them, but there's still going to be a little bit of time error. And remember, we've got 4 different constellations. U.S. time is using its own time, or the U.S. satellites. GLONASS satellites are using their own time. Galileo satellites are using their own time, and the Beidou satellites are using their own time. So there's little time offsets, and these are very small. These are nanoseconds. But remember, it's traveling at the speed of light, so that can equate to some error that needs to be taken care of, right? So we got time error. Then you also have error. I've got the I up there in that thin blue layer. That's ionospheric error. So that thin blue layer represents the ionosphere, which is the part of the atmosphere that gets charged by the sun. So there's electrons in the ionosphere, gets charged up by the sun. Whenever there's solar storms or anything like that, it can get really charged up, and that delays the signal as it passes through that layer of the atmosphere from the satellite to the receiver. That can delay the signal and even distort the signal, okay? And then we have the TR down there in the gray layer. That's the troposphere, and that's the area of the atmosphere where weather occurs. All right, so thunderstorms, lightning, rain, snow, different weather events can have an impact on the signal as well. But when we have 2 receivers and we keep them fairly close together, that's why I got the baseline there. We keep them fairly close together. Most of these errors we can just cancel out, okay? Positional errors, time errors, ionospheric errors, and tropospheric errors can be canceled out because the receivers are seeing the same satellite. And as long as the baseline is close together, and when I say close, usually 10 to 20 kilometers, no more than 20 kilometers, it can be assumed that the receivers are getting the same information or the same errors from the satellites, or as the signal passes through the atmosphere. So those errors can simply cancel out. The positional errors will cancel out, the time errors will cancel out. And as long as we keep those baselines close, it's seeing the same disturbance in the atmosphere, and we can cancel out those errors as well. And that's why if you look at a spec sheet on a GPS receiver, it'll always give a spec like 8 millimeters horizontal, 15 millimeters vertical, and then 1 part per million. So the farther that baseline gets, the more error that's inherent in there, because as they get farther away, they're not quite seeing the exact same amount of atmosphere. If they get way far away, we're going to see a lot of error because we can't cancel out that atmospheric error. So 10 to 20 kilometers is usually what you want to keep your base and your rover apart. Okay. Now, the other 2 errors that really aren't corrected are multipath. That happens when the satellite signal comes down and hits a building or hits a tree and it's bounced. So the signal doesn't come straight to the receiver. It gets bounced over to the receiver. But the signal there, that carrier wave, is polarized, and when it hits something, it reverses the polarity. So the software built into the Trimble receivers is looking for that reverse polarity, and it can cancel out multipath using that technique. And then also the other error that really has to be accounted for in the design of your receiver is just receiver noise. Okay, I've got a radio in here, I've got a cell phone modem in here, I got a computer board and a battery. All that generates noise that can affect how good the antenna can receive the signal. So you need a well-designed unit to help cancel that out as well. So position, time, atmospheric error, multipath, and receiver noise issues, okay? 2 receivers can cancel out a lot of those errors, and then just good survey techniques will help with multipath, and the software in here will help with multipath, and good design will help with receiver noise there, okay? So those are some of the errors that are getting corrected, all right? So when we talk about corrections, that's one of the things that's getting corrected there. So let's take a look at how RTK actually works. And we'll start with base rover, okay? We'll take a look at base rover, network RTK, and Trimble RTX as well. They're all different kind of flavors of RTK, if you will. But base Rover RTK, I've got a control point. Remember in the beginning, we said we're setting a base up on a fixed coordinate or a known coordinate, and we're transmitting information over to a rover that moves around. So the triangle represents a known coordinate, a control point. The circle just represents the survey point. So I've got my two receivers. I've got my base station, and you see an antenna there because we need some way to get information from the base over to the rover. We'll talk a little bit more about that. And then I've got my rover over there with a data collector. That's what's going to rove around or move around and gather 3D information. Then I get my minimum of 4 satellites. We talked about that earlier, right? And they send their signal down to the receivers. Now, one key thing is both receivers have to see the same satellites. If I got 1, 2, 3, 4, let's say the satellite closest to me, if it's blocked by a tree from the base, but the rover can see it, it's still not going to be used because it has to be seen by both satellites, okay? Not as big of a deal nowadays because we have so many constellations up there and so many satellites. But when you start working around buildings, start working around trees, you'll see the number of satellites in your solution drop. Your rover may be able to see it, the base can't, or the base can see it and the rover can't. That's why when you set your base station up, you really need to make sure that you set your base up in the wide open, nothing around it if possible. So then it's getting all the satellites. Then as the rover's moving around in harsher environments, you know, you still got one receiver that's getting all the satellites. Okay. But anyway, I've got my equipment. I've got my satellites. They're all getting signal from the satellites. And then the base station is going to take the raw satellite information, its known position, correction data that we just talked about, how to correct up for errors, and it's going to send that via modem. That's what the little squiggly line is. Going to send the raw GPS data, the known position, and the correction data over to the rover. The rover seeing the same satellites, getting the same raw information. It's going to take the base's known position and the correction information, and it's going to be able to calculate a very accurate baseline or vector back to the base station. And since the base station has a known coordinate on it, now I can get a good known coordinate for the rover, okay? So that's in a nutshell, the basics of how RTK works, using 2 receivers there and at least 4 satellites and a modem to send the correction information over to the rover. So let's look at network RTK. All right, so network RTK, you're just using a rover. And the network has its own base stations that are set up around the state. Like where I am, our state has a network, and there's about 60 or 70 base stations that are set up around the state, kind of spaced out as equally as possible, connected to the internet, and are sending data back to a server, that's a little computer there, in a central location. So they're running 24 hours a day, 7 days a week, 365 days a year, just soaking up raw satellite information and sending it back to a server. Then I go out in the field, little dude with the orange vest on, I go out with my rover receiver, turn it on, start a survey, and I get what's called a NEMA GGA position, which is just a lat long and height for my location. I send that back to the server, and the server creates what's called a VRS, or a virtual reference station, for my location. It uses the base stations that surround my location once it knows where it is, and it creates a virtual base, and that virtual base, because it's close to my location, keeps that baseline length short and increases my accuracy, okay? So even though I'm only going out with one receiver, I'm tapped into via the internet, I'm tapped into a bunch of other base stations. So there's still, you know, that 2 receiver thing set up. But in this case, I've got multiple base stations, so it can actually model out those errors a little bit better. And then I get a correction from the server, either RTCM or CMR, but it feeds me correction data so that I can get a good position at the rover. All right. Then the other flavor we have is Trimble RTX. All right. And that's really come a long way in the last few years. RTX is a satellite-based system. So we looked at base rover, which is all ground-based, right? We have a base station that's using a radio or the internet to send corrections to us. We have network, where we're tapping into the internet to get corrections from a bunch of other receivers. Then RTX It's a worldwide system of Trimble reference stations that are, again, like the VRS, you see the little building/server there, are sending their information back to a server. The server sends that information over to a satellite upload link, which sends the corrections up to a satellite. Then a satellite sends that Trimble RTX correction down to the user in the field, okay? So 3 different ways to do things. Your own base rover, using a real-time network or a VRS network, or using Trimble RTX corrections, all right? We'll talk a little bit more about the pros and cons of each as we move on. So, pros and cons of base rover, right? You're getting a homogeneous solution. I love that word. Homogeneous means you're getting the same thing, right? Every now and then I got to throw out a big word, you know. I went to East Carolina, so I got to make myself sound smart. So let's say I got 2 R980s, right? I got an R980 at the base, R980 at the rover. They're the same type receiver, so I'm going to get the same homogeneous solution from one to the other. That can give you that can just give you a better solution, right? If you're on a network and maybe they're using a different brand that does the math different ways, you might not get as good accuracy with your receiver there. So homogeneous solution can help. Different correction delivery methods. With a base rover, you know, R980 has a 450 radio in it, 450 megahertz radio. It has a 900 megahertz radio, and you can use an internet modem with it as well to send your data. So you've got different ways to send your data back and forth depending on where you are. Greater accuracy, and I throw that in there because generally speaking, you're going to get greater accuracy using a base rover because you're using the same equipment and you're using shorter baselines. Okay, and those shorter baselines are going to give you greater accuracy. And that allows you to work in harsher environments. We see our customers putting a base station, their own base station, out in the open and being able to take their rover, say, into the woods or into urban canyons and get greater accuracy, greater precisions in there because of the shorter baseline and because they're using like receivers. And then you're in control, right? It's your stuff. You'll have to worry about the network being down or some problem with that going on. So what are some of the cons of that? Obviously, you have to buy 2 receivers, right? With RTX and network RTK, you only have to have 1 receiver. You're using somebody else's stuff. So the cost, the security of an extra receiver, depending on where you live, it might not be safe to leave a base station sitting out, right? People might steal stuff where you live. We have that happen every now and then in our territory. And then again, it's just more equipment to keep up with. And then also the range from the base. Radio has limited range. Again, you've got your PPM error you got to worry about. So you have limited range you can go. So on a larger project, it may not be as practical to have your own base set up, right? So let's look at some of the pros and cons of network RTK. So less initial cost, obviously, and less equipment to keep up with. The range is better anywhere inside the network. So like I said, I have a network that covers my whole state. I can hop out of the truck anywhere in the state that I have internet connection. That's one of the cons. And I can work off of that one end of the state to the other, right? And then modeling. You know, we talked about how 2 receivers cancel each other's errors out in a small area. Well, when you're using a network RTK and especially a Trimble network with pivot software, it's doing some really advanced modeling. And since the network covers the whole state, it's sampling a lot larger data area than just 2 receivers together, right? So that helps you in times of solar disturbances and things like that. So some cons, accuracy, because the base stations are spread out a little bit, even though it's creating a Trimble network's creating a VRS, the accuracy is usually, just generally speaking, not quite as good as a base rover being close together. All right. And then the strength of the network geometry, where you work matters, right? If you work in a coastal area and the network ends kind of inland, you might not have good geometry that surrounds you, and that can cause problems. Network availability and solution, right? If the network goes down, you're not working off the network. You know, that happens sometimes. And then the solution, you know, some networks may not be as advanced as your receiver. They might not have all the constellations. They might not be putting out as many corrections. Remember, it's got to be the same at both. So if you're if your network's only putting out corrections for 2 of the constellations, your rover's only working off of 2 of the constellations, even if it's capable of all 4. So that's another one. And then you're dependent on an internet connection, right? This is all internet based. If the internet service goes down or you're working in an area that doesn't have internet, that's going to affect you as well. So let's look at some pros and cons of Trimble RTX. So one of the great things about RTX, freedom to work anywhere. It is a true global solution. So you could pack up and go to another country, hop out with your Trimble gear, and be able to get corrections from RTX. You don't need a base station again, so no extra receiver, no less to keep up with, and you get global modeling now instead of just 2 receivers, canceling out air, a VRS network covering a larger area. Now you actually get global modeling because Trimble's got reference networks or reference receivers for RTX all over the world. So that gives you even better. And then, you can use it as a complement. So you can use your base Rover, you can use your RTN, and if you have trouble with either of those, you can turn to RTX. So what are some of the cons? Not as accurate as base Rover RTN. So base Rover is really the most accurate we've seen. RTN would be second, and RTX would be next. Now, RTX isn't bad. It's rated for 2 centimeters horizontal and 3 centimeters vertical. So in a lot of situations, that's all you need. So it's still a very good solution. And then our customers have told us it's not as robust in challenging environments. So maybe getting around the woods, getting around buildings, it doesn't usually work as good because it's dependent on seeing that satellite up there, and you're kind of losing some of that when you get around harsh environments. So yeah, you may not be able to see that RTX satellite. You can use RTX with internet, so you can get those corrections via the internet, but of course then it's tying you to the internet, right? So let's look at some of the equipment that we have to offer for you guys doing RTK. Right now, the main receivers we're using on the survey side are the R980, the R12i, and the R780. So really, they all have 3 things in common. They all have tip technology, which we'll talk a little bit more about in a minute. They all have ProPoint GNSS, which we'll talk about, and they all have Trimble IonoGuard. Now, IonoGuard is really important because this is 2025, and 2025 is a solar maximum. So every 11 years you have solar maximums. There's more solar storms that can delay the signals as they come through the ionosphere. Trimble has, with the latest software for these receivers, Trimble has written into the firmware something called IonoGuard that can help mitigate those solar events. So that's a big advantage to using a Trimble receiver there. Now, some of the differences, the R980 has a 4G LTE modem in it. So if you're sending your corrections from the base to the rover and you want to do it via internet, you can put a 4G compatible SIM card in the receiver and do it that way. It also has a dual band 450 megahertz radio and 900 megahertz radio. So, depending on who you have to communicate with radio wise, you've got 2 choices there. The R12i, which I happen to have here, the R12i, it just has a 450 megahertz radio. So it doesn't have that LTE modem and doesn't have the dual band radio. The 780, which I don't have one with me today, the 780, it has the tip, the ProPoint, the IonoGuard. It also has, or you can get it with a 450 and a 900 radio. The big difference with it is it can be a little bit cheaper because it's configurable. So these kind of come with everything, right? A 980, a 12i kind of come with everything. But with a 780, I can buy it as just a base station, and then it will only work to get satellite data and send it to a rover, or I can get it as just a rover and it can only receive information as a base, or you can get it where it'll do both, okay? But the 980 and the 12i, they'll both do both, so you can use them as a base or a rover. The 780, you can do both, but you save a little bit of money by configuring it for one or the other and do that, okay? So then we also have one option that's a rover only, and that's the Trimble Catalyst survey. And if you look, that's just a little plastic antenna called the Trimble DA2, uses an external battery there that you can see, and will work with Trimble Access running on a TDC6 or a TSC5, and it still has ProPoint. It doesn't have tip, doesn't have IonoGuard built in, but it does have ProPoint. It supports all the global GNSS systems. You do have to have a Trimble Access Catalyst survey subscription to use this. So it is a subscription-based service. And that will run off of RTX, or it'll run off your local VRS network. Okay, so again, that's a Rover only, kind of a little bit less robust, doesn't work as good in harsh environments, just a less robust but more cost-effective solution that is available there. Excuse me. So there's also just permanent base stations. So some of our customers like to have a base that is set up and just running all the time, right? So we offer the R750 or the Alloy. Both of these have ProPoint and IonoGuard built in. The 750 there, the yellow one, actually has a 4G LTE modem built in. It can be hooked up to the internet. It can be hooked up to an external radio, and it also has an internal radio, okay? It could even be used as a Rover if you had to. It's a little bit heavy. I don't know anybody would want to carry it around, but it has a little bit more built in, right? So it's a little bit more flexible to use as a base outside an office environment, if you will. The Alloy is really to be made to be set up in a building, connected to the internet or an external radio to pump corrections out that way. And then, both of these would run a cable up to a antenna that would be placed outside the building. So these are permanent bases that you can use as well. So know that you can use portable bases or permanent bases depending on what your workflow needs to be. So let's talk a little bit about some of those buzzwords I threw out there, like Trimble ProPoint. So Trimble ProPoint is capable of using all the GPS signals that are out there. GPS, GLONASS, Galileo, Beidou, SBAS, RTX, it can basically use everything. And that results in a very flexible system that works well in all environments. So it's constellation agnostic. Basically, whatever satellite system it sees, it just starts dumping all of that satellite information, starting with the first one it sees into one filter. So it doesn't split it into like processing GPS only, processing, and then augmenting that with GLONASS or augmenting that with Beidou. It combines all the satellites into one, which gives us a better estimate of outliers and allows us to work in harsher environments. So getting into the woods with these, I spent 18 years telling guys, don't go in the woods with your GPS, you'll get bad results. Well, now you can push up into that tree line and see fairly good results. You do have to keep an eye on it, but you can see fairly good results. You can work in urban canyons with tall buildings around you, or even down in valleys that would block the sky before, because ProPoint and all those constellations can create corrections that will give you good data. All right. And then TIP technology. TIP technology means that these receivers have IMUs built in, inertial measurement units. So instead of calculating the position at the antenna phase center, it's calculating for the tip of the rod. So as this moves around, it knows the length of the rod. And as this moves around, it's actually doing the calculations for the point on your rod, because that's where the measurement's really being taken place, right? So what does this do? Allows for faster surveys because you don't have to plumb the rod up anymore. Easier stakeout, because instead of having to plumb the rod up and then move and plumb the rod up and then move, I can just keep moving the tip till it tells me it's good and I never have to plumb the rod up. Safer location. I can reach the rod out over a guardrail into the street. Access to hard to reach locations. You can do an offset by holding it up against a tree and giving the direction based on how the receiver's leaning, or reaching over into a creek like he's doing there. So let's talk about some of the different ways that we also have equipment-wise for getting our corrections over to the Rover, right? To the Rover. So that's some of the hardware that we use as far as receivers go. Some of the other stuff we need to be aware of are radios. We have external radios, which are larger radios, more powerful, can go a farther distance. You set those at the base, connect them to the receiver, and that will broadcast those corrections to the Rover via the external radio. Then we also have internal radios. You'll see the antenna on the receiver there. The antenna just screws in here, so you have an internal radio, less powerful, shorter distance, right? So two ways to use radios. You can use external or internal. And then we can also use the internet. So with the internet, you can use something like a MiFi hotspot connected to the base to send those corrections to the Rover. You could use a SIM card, the 980, on the 980 anyway, you can plug a SIM card in and use that. And then you could also use like the hotspot, the Wi-Fi hotspot on a phone, okay? So multiple different pieces of equipment out there that we can equip you guys to do very accurate RTK survey with. We've got units that can act as a base and a rover. We got units that can act as permanent bases. We've got units that can act as rovers only, and we've got multiple different modems that can get your data from the base to the rover, depending on how you work. And we have RTX, which just uses a satellite, so you don't even need a modem, right? So let's kind of wrap this thing up here. So we talked about RTK, what it is. We talked about how it works, showed you guys different types of RTK and different equipment. So now what I want to tell you guys is don't forget to turn on your notifications, because we're going to start working on these getting started guides immediately. And over the next few weeks and months, we're going to get these posted to playlists, getting started guides with 980s in Trimble Access, doing base rover, getting started guides with 980s in RTNs, getting started guides with Access and S7s, getting started guides with Access and an SX12. So we're going to be working on getting back to basics, getting you guys these getting started guides so you can be successful with your Trimble equipment. So hey, thanks for sticking with me on this one. Look forward to getting back to basics in the future. I'll see you on the next one.